All right, so if you'll recall from a previous lesson, the definition of a derivative, which your derivatives are written as f prime of x, this is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And just a little quick review, if you have a graph right here and you have a function that does some curve or something there, we're going to have a point at x and its y value corresponding to that will be f of x, and we're going to have another point at x plus h, and its corresponding y value would be f of x plus h. And so what you're looking at then is h is the distance between these 2 points. And if you were to graph a secant line, it would go through those 2 points. And we can find the slope of that secant line simply because we have 2 coordinates, change in y over change in x, calculate it just using your slope formula. However, if we want to find the slope of the tangent at this particular point, that tangent would go like this. It just touches that curve at one point. And as this point moves closer to this other point, but still stays separate, as this point moves closer, this orange secant line will become more and more like the tangent line. And so that when this point gets extremely close to this other point, we can still calculate the slope because we have 2 points, and that slope will be approximately the same thing as our tangent line right here. Now the idea here then is, in order to get precisely what the slope of this tangent is, we want this h value, which is the distance between these 2 points, we want that h value to approach 0 so that the distance between the 2 points becomes negligible. All right, so that's where this comes from, is the limit as h approaches 0. We want those 2 points to get closer and closer together, and this is just your formula for slope. It's change in y, because you have f of x plus h minus f of x, that's the numerator, over change in x, so delta y over delta x. If you take this point and subtract that point, the x's will cancel, which leaves you with just h in your denominator. All right, so what we're going to do now is we're going to take a look at how this concept can be tested on the AP exam, and how you will often see the notation for this. All right, so let's take a look at this first problem here. This is asking for the limit as h approaches 0 of this whole mess right here. Now, we really don't have to understand what this whole thing what this whole thing is and how to work it out. We could, theoretically, we could take this and raise it to the 4th power and expand it all out and combine like terms and then find the limit by substituting 0 in. That is a very long process. What we want to do is recognize that this is simply the definition of a derivative. If you remember, the derivative had f of x plus h up here, and you see this x plus h, that's a clue that you're talking about the definition of a derivative. So let's refresh something real quick here. If you had, for example, f of x is equal to 4x raised to the 3rd power, and you wanted to find f of 5, well, all you would do is take that 5 and plug it in to the x. All right, so that means if we want to find f of x plus h, what you are doing is plugging x plus h in for the x. It's just the same thing you do with the 5. So we're plugging x plus h in for the x, which would give us 4 times x plus h to the third power. That's the idea here. So remember that this up here, this represented f of x plus h minus f of x in the numerator. All right, so this part right here is our f of x plus h. And so what we want to do is, since we recognize this is the definition of a derivative, we got to figure out, first of all, what is the function that we are taking the derivative of? Well, if you see x plus h, what that means is that x plus h was substituted into your x. So originally, this was just an x right here. So the function would be 3x raised to the 4th power. And we have an x plus h here also, which would have originally been an x, but x plus h was put in its place. So that gives us plus 2x. Now the rest of this stuff over here we really don't need to pay any attention to right now. That does represent f of x, but I don't want to emphasize that part of this at this time. We want to look at how do we handle this problem here. So this is the definition of a derivative. We know the function now, so the last thing that we need to do with this is actually calculate the derivative, which you can use your power rule, and this ends up being 12x to the 3rd power plus 2. And that is what this whole mess up here is equal to. All right, so another example with this. Once again, we should recognize this is the definition of a derivative. So the first thing is to figure out what is the function we are taking the derivative of. And so we figure that out by seeing these x plus h's, and we're going to replace those with just x. That will make this 2x raised to the 3rd power. And then we're going to have minus 5x to the 2nd power. All right, so now we take the derivative of our function, and that will end up being 6x squared minus 10x. That's it. That's what this stuff right here is equal to. And that is just, once again, the slope of the tangent line at any particular value x. Now this is just a different way of notating this. In the previous examples I used h as the distance between the two x values. Sometimes they will use the notation of delta x instead of h. Doesn't mean anything different. It's the same exact thing. So this is still the definition of a derivative. We need to first identify what the what the function is. So that's going to be 7 times x squared, because once again we're replacing this with x. And then we're going to replace this with x, which gives us plus 2x. And again, we're going to ignore this last part of this right now. I'll show you how that's going to come into play in a little while. All right, so the next thing after finding the function is to find its derivative, and that would be 14x plus 2 using your power rule. All right, so what's different about this problem? Well, one of the things that you should notice is that it looks like definition of the derivative, but there's no x in this anywhere. And there's no f of x in this anywhere. This is still the definition of derivative. This is something plus h. This 6 just simply means that our x value was 6. That's all that means. So normally we would have had x plus h here and here. So we can get our function from here just like we did before. So our function would be x to the third power minus 2 times x. And the derivative, therefore, is 3x squared minus 2. Now, this right here adds one more step to our process. When you see the 6 instead of an x, this simply means that we are evaluating the derivative at the x value of 6. All right, so that's going to give us 3 times 6 squared, which is 36, minus 2. That's 108 minus 2 is 106. That would be the slope of the tangent line. Now, remember before I said not to worry about this stuff over here when trying to figure out what your function is. I said concentrate on the stuff plus h when it's something plus h, because even if they put a number in place of the x, we were still able to figure out what the original function is. Over here, this is where we had minus f of x. Well, with just a number here, we can't figure out what the original function really was to start with, because what they have right here is not f of x, it's actually f of 6. And that means if we took 6 and put 6 into that function, you would get 6 cubed, which is 216, minus 2 times 6, which is 12. That's the 204. That's where this value came from. So this part right here, that's f of 6 plus h, and the other part is f of 6. All right, so let's take a look at one more problem with this. And so we're going to first write down what the function is. All right, so f of x would be 2x raised to the 4th power minus 5x cubed. Then we take its derivative, because this is the definition of a derivative. That would be 8x cubed minus 15x squared. But once again, you'll notice that there is no x value. What we have is a 3 in its place. So that means we're going to be evaluating this derivative when x is 3. All right, so that's going to give us 8 times 3 cubed, which is 27, minus 15 times 3 squared, which is 9. All right, so 8 times 27 is 216, minus 135, which comes out to 81. All right, so on this, this is just a refresher on how to find the equation of a tangent line. We've discussed this one before. You want to use the point slope form for an equation of a line. And with the point slope form, there are two things that you need to always find. You need to find the coordinate of a point that is on that line, and you need to know the slope of the line which is also the derivative, evaluated at some particular number. In this case, the number we are evaluating the slope at is at x equals 1. And that also tells us the x value for the point that we're going to use is 1. Now, to find the y value for the point, we're going to take that 1 and substitute it into our function where you see the x. So that's going to give you 1 cubed minus 4 times 1 squared plus 3, which ends up being 0. Now, what we need to do is figure out, well, what is our derivative in terms of x? Well, the derivative in terms of x would be 3x to the second power minus 8x, and derivative of a constant is always 0. Now we evaluate that derivative at 1. Once again, this is just a generic relation that will tell you what the slope at any point on that graph is. And so if we want to know the specific slope at a particular point, all we have to do is plug in the point that we're referring to. In this case, that is 1. So 3 times 1 squared minus 8 times 1 is going to give us negative 5. We can now build the equation, which will be y minus y1, and the y value is 0, so that's going to just drop off, equals m, which is our slope or derivative, times x minus the x value, where in reference here is 1. And you can leave your equation like this. If you want to distribute it, go right ahead. It doesn't make any difference. All right, so the next thing that we're going to take a look at then is how we can use that tangent line to approximate values on a function. And for this problem, we're going to use that same function that was on the previous slide, except instead of using it at x equals 1, we're going to be using the tangent line at x equals 0.5. And we're going to use that tangent line to approximate f of 0.51. And then we're going to take a look at the approximation and determine if the approximation that we have is an overestimate or an underestimate, and determine why we know that answer. All right, so just to give us a little bit of information here, if you have a curve on your graph and we're trying to look at a point right here, for example, and we've got a tangent line, and let's just say this is on a graph somewhere, and this value is at 0.5. 0.51 is going to be a little bit to the right of that, which means if we follow that up, we're going to have a point here and a point right here. This point right here is the actual value. That is f of 0.51. The point that's up here is the approximation. What we are doing is we are using the tangent line to approximate a value. That value should end up being pretty close to this value because the equation of the tangent line was derived at the point 0.5. That's super close to 0.51. Because these two numbers are real close to each other, these two values are going to be close to each other. Now, naturally, if I wanted to use this tangent line to evaluate when x is 6, that would be way over here. The tangent line would be way up there, and this parabola would be way down here. That would not be a good approximation. All right, so it's only a good approximation because this number that we're approximating at is real close to the point of tangency. All right, so let's see how this works out on using Desmos here to take a look at this. All right, so there are actually 3 points that are on this graph. The red graph is the one that we were using earlier. Just graph that. The blue line is the tangent line at x equals 0.5. And so we have 3 points located on that graph. There's a green point, that is the point of tangency. There's the red dot, which is f of 0.51. That's the actual value of the function. And then we're going to have a blue point that is going to be the tangent line approximation. Now, they look like they're at the same place pretty much, but if we zoom in to this, we can start to see a little separation here, and we can see that, yeah, the approximation point and f of 0.51, they're going to separate from that point of tangency, so it's a little bit off. But the f of 5.1, the red and the blue dot, are actually still really close to each other. So I'm going to have to zoom in a lot in order to actually get some separation here. All right, so now, after zooming in a lot, I can actually finally see the separation. And so the red point is on the actual curve of the function. The blue point is on that tangent line. And you can see that the blue point is a value that's higher than the red point. What that means is that we are going to have an over approximation of the actual value. All right, so if we think about what's happening here with this, if you look at a graph that's curved down like this, and you have a tangent, and it doesn't really matter where the tangent is, you got a tangent. Notice where the tangent line is located. The tangent line is located above that curve, no matter where you put a point. Therefore, if you use a linear equation to approximate a value, that approximation is always going to be an overestimate because it's going to be higher than the actual value. Now, if you have a curve that opens like this, then when you do a linear approximation, you can see if you pick a point, the approximate value on the line is going to be lower than the actual point that is on the curve. So when you have this kind of situation where the curvature is going up like this, and there's a word for that, we'll put that here in a second, then the actual value is going to be higher. So that means that we have an underestimate of the actual value. All right, so let's take a look at one more example here. We're going to use the tangent line at x equals 3. So we're going to use the same function, but we're using it at a different point on the graph. We're going to use a tangent line at x equals 3 to approximate f of 3.01. And once again, I am using a point that is real close to my point of tangency, which means it should give me a pretty accurate approximation of the actual value. All right, so let's again use Desmos and see what the graph looks like here. All right, so we've got the same graph and we've got the same 3 points, but notice our tangent line is at a different location. The tangent line is at x equals 3 on this one. But we're going to approach this the same way. Let's start zooming in and see what's happening at this particular point. Okay. So the point of tangency and the other 2 points start separating from each other, but we actually have to zoom in quite a bit more to actually start to see some separation. All right, so remember, the red is the actual function, the blue is the approximation, and the approximation is under the actual value. So this is an underestimate of the actual value. So this is your situation where you have a curve that goes up, and we've got a point on this, and so we have an underestimate because it is underneath the actual value. All right, this is going to lead us to some conclusions here. If a function is, and this is where that new term comes in, of concave up. Concave up means it looks like this. Then the linear approximation is going to be an underestimate. Because your tangent line would be under that curve. And if your function is concave down, which just means your graph is opening down, then your linear approximation is going to be an overestimation. Because your tangent line is going to be above the curve. Now, at this point, we really have not talked about concavity. This is just the beginning of it. There are some ways using calculus to determine where a graph is concave up or concave down, and that involves using our second derivative. The rule is wherever your second derivative is positive, your graph or your function is going to be concave up. And wherever your function, the second derivative, is negative, your graph is going to be concave down. So that's just a taste of things to come.